A-level physics. What is the induced EMF? And I'm not going to lie, this one caught me out because what I did was the common mistake was I tried to find the area of this face. So what I did was 5 times by 10. But that's not what you do, because you have to remember about what orientation do we want these to be at in order to get our EMF induced, in order that magnetic flux linkage to be a maximum. Okay? So if you find this video useful, remember you can always join our exam master classes. We give you lessons coming up to your exams and the night before your exams, all for just 59 quid. It's 15 hours in total. So to join us, just click the link in the bio. So the way I think about these questions is always, there's my magnetic field lines. I would always draw this in my test and draw a coil of wire, kind of an angle, and then draw the normal. Now we know that the magnetic flux is always going to be a maximum. So magnetic flux, we use this symbol, right? So magnetic flux is going to be a maximum. Magnetic flux is B times A. B is my magnetic flux density. So basically it tells me like how strong the magnetic field is in that area. And A is the area of my coil of wire. So magnetic flux is maximum when the normal is parallel to the field lines. So normal is parallel to the field lines, right? So what we're saying then is I want the plane of the coil, so there's my plane of the coil, to be perpendicular to my field lines, okay? So we look here, if I look here, that plane of this face, that face is parallel to the field lines. So that's not the face we care about. We want the face, the plane that is perpendicular to our field lines. So this is the area we care about, right? We want it to be at right angles to that field lines, okay? So again, it's the magnetic flux is a maximum if the normal is parallel to the field lines. So again, the normal of this face will be there. The normal is parallel to my field lines. Or another way to say that is the plane is perpendicular to those field lines. So that's the area we care about. So when I find the induced EMF, I know the induced EMF is equal to the rate of change of the magnetic flux. Magnetic flux linkage, because normally you've got these multiple turns of coil. But we don't have multiple turns of coil, right? We just have our face of our box. So our box is moving at a constant speed through this magnetic field, this uniform magnetic field. To get the EMF induced, I need to do B times A. So B is 2 milliteslas, 2 times 10 to the power of minus 3, times by the area. So we're doing the area of this face. Now the area of this face is 30 centimeters by 5 centimeters. So what I'm going to do is 30 centimeters times by 5 centimeters. So we're doing 30 times 10 to the power of negative 2 times 5 times 10 to the power of negative 2. And we're dividing the time it takes to go through that field. Okay, now I'm thinking, how do I get the time to go through the field? I know the speed it's moving at, and I know the distance that it's moving through the field. So I know if I have a speed equals distance divided by time. So a time is a distance. The distance it travels is 30 centimeters, 30 times 10 to the power negative 2, divided by the time, divided by the speed, when you arrange this, which is 5 centimeters per second. Because it's in centimeters per second, and this is in centimeters, I don't have to change my units. So I could do 30 centimeters divided by 5 centimeters per second to get my times in seconds then. So I do 30 divided by 5, I'm going to get 6. So I know my time is 6 seconds. That's the time it takes for this box to move through that magnetic field. So my time then is going to be 6 seconds. So all I'm going to do now is my 30 times 10 to the power negative 2 multiplied by 5 times 10 to the power negative 2 to get the area of that face. I'm going to multiply by 2 times 10 to the power negative 3 because it's my magnetic flux density. And I'm going to divide it by 6 because that is the time that it moves through. So I get is 5 times 10 to the power of negative 6 volts.